Yes. Uh, so it seems to me that last time I said something very wrong, namely, we consider the whole algebra H, well, in a sense of O, and I don't remember exactly, but maybe I claimed that it's isomorphic to the split K theory of finite or modulus, but certainly it's not isomorphic. So here a basis is formed by just isomorphism classes of modules, finite or modules. And here the basis is formed by indecomposables. So here base is numbered by positive, non-negative integers, and here the base is numbered by all the possible partitions. Okay, and now last time I formulated a theorem about universality of structure constants, theorem 2, that there is an isomorphism of algebras like this, where the generator VR goes to Q negative R choose 2 ER, elementary symmetric function, and VR was the class. Yes. Yes. I am just in the process of formulating it. So VR is the class of trivial, well, elementary module of length R. And under this isomorphism, there are polynomials g lambda mu nu of t with integral coefficients, such that the structure constants in the whole algebra with respect to the basis u lambda. These correspond to the isomorphism classes of or modules. These structure constants, well, G, capital G, lambda mu nu of O, are just specializations of these universal polynomials when T equals Q, the cardinality of the residue field. And this was part 1. And part 2 was that the degree of these universal polynomials is at most n of lambda minus n of mu minus n of nu, where n of lambda is the sum of I minus 1 lambda I. And the last claim is that the coefficient of g lambda mu nu of t of this degree, a priori top degree, equals c lambda mu nu. So the Littlewood-Richardson structure constant. With respect to, well, so S mu equals the sum of C lambda mu nu S lambda. Okay, so this is the theorem we are starting to prove, but it's unlikely we finish the proof today, maybe in a week. Not that I will give an explicit formula for these universal polynomials, g small, but I will instead I will give an explicit formula for something else, and it will suffice. But in order to formulate this explicit combinatorial calculation, I need another notion of compositions and arrays. So, well, we already encountered compositions. So a composition alpha equals alpha 1, alpha 2, and so on. And then eventually it becomes all zeros. So it's a finite sequence of non-negative numbers. So there is a natural action over S infinity. So these are permutations of n identical almost everywhere. There is a natural action of this group on the set of compositions. Just we permute their entries, yeah, and each orbit, well, S infinity orbit, contains a unique what? Pardon me? Right, partition. So compositions are disordered partitions. And graphically, yes. Mm-hmm. Yes. So this is alpha 2, alpha 3, alpha 1. Then alpha 4, alpha 5. So I think you are absolutely right. Alpha 6, and so on. Yeah. Okay.
So this is the definition of S sigma infinity. So it permutes on a finite number of
Right.
elements.
Yes.
Okay.
And S alpha is alpha S inverse of 1, alpha S inverse of 2, and so on. Okay. Now, this would be called the diagram of alpha. So this is a subset of Z squared. Namely, it is the set of pairs I, J, such that 1 less than J less than alpha I. Pardon me? Well, yeah. And this is, as I mentioned, in the very first class, there's the English notation. But by the way, it's an aside. If you had a look at your home assignment about bijection of Schubert cells and partitions, just indexing Schubert cells by partitions, so there was a box K by L, and there were partitions inscribed inside. So this was like, only I forgot, I always forget. Probably it's B0, and then it's A1, and then it's B1, and then A2, B2, A3, and maybe then the next B is 0. So this is our diagram. And this way of presenting the diagrams is called Russian way. Or in Russian notation, probably in honor of Andrei Zelevinsky. And those, well, lambda written in terms of A's and B's is called Frobenius coordinates. Of a partition lambda. Okay. So the Russian way is the English way rotated by 135 degrees or something like this, approximately. Okay. So now we are discussing compositions, and given compositions alpha and beta, we say that an array of shape lambda and weight beta. So it's a sort of generalization of tableau. compositions are generalizations of partitions, and arrays are generalizations of tableau. Is a way to fill in the boxes of oh, sorry, alpha, yes, sorry. The box of alpha with positive integers. Such that I occurs exactly beta I times. Okay, so in other words, such an array is a function A from alpha to positive integers, such that the fibers have cardinalities prescribed by beta. Now we can, and we will, extend A to a function on the whole over M2 by assigning A of I, j equals plus infinity for j bigger than alpha I. So we have some numbers written here and infinity everywhere else. Okay. Now it's a big luck that today is Tuesday, and we have 4 blackboards because we will need all this notation. Accept my condolences. So for x, a box we set x right is I j plus 1. So the next box to the right. X, this x right. Okay. Now we say that an array A is row ordered. Or maybe even strictly row ordered if A of x right is at least A of x or strictly bigger than A of x. Well, there are also column ordered arrays. And one last thing, we introduce a complete or total order lexicographical. Order on the set of boxes. So we say that a box ij is less than I prime j prime if j is less than j prime, or j is equal to j prime, and then I bigger than I prime. So well, we go along the rows like this. Lexicographical. Yes, lexicographical. Yeah, so anything, well, maybe I shouldn't do it this way. Anything in the right column is bigger than anything in the left column. And in the same column, pardon me? Yes. So yes. So we go like this inside one column, and from one column to another column, like that. Okay. Now, for an array A, strictly row ordered, we set D of A is the number of boxes, of pairs of boxes, such that y is lexicographically less than x, and a of x is less than a of y, less than a of x right. Yeah, so well, y is maybe this is x, this is x right, and where is y? Approximately. Where should we look for y? Y is less than x, so what does it mean? Yeah, so yes, it could be, well, here or here. Either to the left or right down below.
But in this case, y is not bigger than x, no?
Pardon me?
Well, if we put y
Yes.
on the left side from x, on the left column,
Yes.
it is not bigger than x.
It's smaller.
But it should be bigger than
It should be bigger. Sorry. Yeah. So vice versa. It should be here. Either to the right or above, yeah? Either here, right above, or somewhere to the right.
Well, if it's too much right, then smaller than x as a symmetric.
No. The value of this function a should be smaller. For y itself, its position is only compared to x.
But in this case, shouldn't x and y be in the diagram?
Yes, they should.
Okay, so the picture doesn't.
Mm-hmm. There is some big diagram containing everything. Y cannot be. So y is bigger, smaller than x. So it still should be to the left. Sorry, I'm all confused. So it should be to the left or below. So it was correct before. Sorry. Mm-hmm. Yeah. Yes. A should be row ordered, but it's another condition. It has nothing to do with position. A grows to the right. Mm-hmm. Nothing. Well, it could be also nothing, no condition. Okay? No, it's an extra data. Array is a composition plus filling with numbers. The numbers should grow along the rows. And so on. Yes.
Тогда опечатка, наверное, и вторая строчка снизу, там и меньше. Потому что если слева направо возрастает, то все это просто
Да, потому что у нас получается, если мы идем вверх или вправо, то у нас
Yes.
по возрастанию. Нет, нормально как раз. У нас
I don't know.
меньше, то есть мы идем вверх. У нас же и чем больше,
мы
тем
хотим,
дальше.
чтобы левая клеточка была меньше, чем правая.
Да, левая, а это жи.
Нет, это и.
Нет,
вот
это жи.
так это и, а вот так это жи.
Нет, у нас вертикально.
Here is J, here is I. So maybe we'll see it later, but so far it's just definition. Pardon me?
So intuitively, which cell is bigger than the other?
Just I drew here.
So figure is less, y is less than x?
Yes? If it's either to the left or strictly below. Well, this is J, this is I. This is our standard notation for partitions. It's lambda 1, lambda 2, and so on. It's English notation. There's a French notation where I goes up. Okay. Pardon me? Yes.
Ну, то есть не в правом верхнем квадранте.
And the conditions on the filling.
Так. Вот с от x не очень просто понятно, как мы ее строим.
It's an extra datum. Like you can fill in a Young diagram with numbers to obtain a tableau. The same way you can fill in a composition with numbers to obtain an array.
То есть и мы
No, no, we only can consider row ordered. No conditions along columns, only row ordered. Okay, so now I formulate proposition 3. So let lambda and mu be partitions, and alpha beta compositions. So alpha is in the same orbit as mu, and beta in the same orbit as lambda transposed compositions. Then I'm afraid I didn't recall what is a lambda mu. Well, let me try to fit them in here. So a lambda mu is the set of the cardinality of the set of flags M of type mu. Well, it is equal to M0, contains M1, and so on, contains MS, which is 0, such that the type of mi over mi plus 1, sorry, m minus 1 over mi is it's elementary, lambda I transposed. So this quotient is elementary. Like the uniformizing parameter z or p acts trivially on the associated gradient. Okay, so these are coefficients we encountered last time. We already noticed that they vanish unless lambda dominates mu. And now I claim that a lambda mu is the sum over all arrays q to d of a. So the sum over all a of shape alpha, weight beta, strictly row ordered. Okay, so here is the proposition, and it is roughly of the flavor we need. Yeah, because such a lambda mu is a particular case of the structure constant, namely when we multiply just elementary modules. Yeah, and now I claim that this structure constant indeed is a universal polynomial in Q, in the cardinality of residue field. So that's at least consistent with what we are going to prove. But yes. They're in the same orbit of symmetric group. Okay, so on the one hand, this is well, a strengthened corollary of our theorem. So from our theorem, it follows that there should be a polynomial, and now I write down this polynomial explicitly, in a sense. On the other hand, this will imply our theorem. It's enough to know just this, and this I will explain. So let us derive theorem 2 from proposition 3. Well, let us denote a lambda mu of t by definition is the sum of, just like here, t to d of a over the same set of arrays. Then I claim that the following three statements hold. So first of all, a lambda mu of t is a polynomial with non-negative coefficients. And this is obvious. Second, the value of this polynomial at 1 equals the cardinality of the set of matrices with entries 0 or 1, so like fermionic matrices with row sums mu1, mu2, and so on, and column sums lambda 1 transposed, lambda 2 transposed, and so on. And finally, this polynomial a lambda mu of t is 0 unless mu is dominated by lambda. Now, note that by property A follows by definition, just because we sum up monomials. Yeah.
But how do we know that all the t of A are different for different A's?
Pardon me? Say it again. So indeed, A is obvious. But now, granted B, C would follow absolutely combinatorially. In fact, we already know this. I will recall it in a moment, but we already know this. Because if there's a polynomial with positive coefficients, if it vanishes at 1, then it must be identically 0. So A is obvious from definition, but very strong. Okay. Now let us see why this is so. What can I erase? Maybe everything except for this. Yeah. We construct a bijection from the set of arrays A as above to the set of matrices as above, I mean such matrices. Yeah, and the bijection is as follows. A goes to the matrix Cij. So Cij is 1 if J occurs in the ith row of A, and Cij is 0 otherwise. Okay. So
now, as I explained, if you believe this, so this proves B. And as I explained, it reduces C to a purely combinatorial claim, which we, in fact, already know, but I will recall it. I mean, we already mentioned that number of such matrices is a matrix coefficient of some transition matrix from monomial to elementary symmetric, symmetric functions. So, well, given B, C follows from the Gale-Reiser theorem that if we consider the transition matrix from monomial to elementary symmetric, then its matrix coefficient like this is 0 unless lambda transposed is less than mu transposed, or equivalently, lambda is bigger than mu, dominates. Okay. And let me recall why this is so. This transition matrix. So on the one hand, we prove that it's a product of two constant matrices. So lambda mu is matrix coefficient is the sum over nu Kostka numbers k mu lambda, k mu transposed mu. And on the other hand, this is the number of matrices above. For the following reason. So if you consider E lambda, there's E lambda 1, E lambda 2, and so on, has x to the power mu with the following coefficient. So any monomial in E lambda has a form, the product over J, xj to Cij, where Cij is 0 or 1, and the sum of Cij over J is equal to lambda I. This is clear.
just by definition of the elementary symmetric functions. Hence, the product over I and j of xj to the power cij is equal to the product over j of x j to the power mu j, where the sum over c I j over I equals mu j. Okay, and this is just what I said. So we count the matrices with row sums lambda, mu, column sums lambda, and such a count gives us the transition matrix entry lambda transpose mu.
Okay.
Okay. So we proved those three claims, A, B, C. And I promised to deduce theorem 2 from proposition 3. No, this was an aside. I can forget it. Just we once wrote a big table with all the transition matrices, and we expressed all of them through Kostka matrices, and this was one of the. And we also argued that all such matrices were, well, not all, but most of them were upper triangular or lower triangular. Yes. К массивам, to arrays. Well, there is a bijection here. Arrays are the same as such fermionic matrices. Okay, in particular, yes. Well, there are finitely many such arrays and finitely many such matrices, and they are in bijection. Well, this matrix is not necessarily square matrix. It depends on the length of mu and length of lambda transposed. If they are the same, then the matrix will be. Yeah. Okay, and now the this just because we are considering coefficient of x to the mu of this particular monomial. So inside here, we well, any monomial in here looks this way, but we're only interested in this particular monomial of this sort. So there is this condition, evidently. That's it. Nothing clever. I think we already discussed this in class, or maybe you solved such an exercise in your home assignment. So that's just a recollection, in my understanding. If you just look through your notes or through McDonald's book, you find that hopefully we discussed this. Or maybe it's my imagination, but anyway, it's similar to what we discussed. Okay, so now I promised to deduce a theorem which I'm about to erase from proposition. So let me do this. So proposition 3 implies theorem 2. Why? Because last time we already proved that A lambda lambda is just 1. And now we proved that this matrix A lambda mu is strictly lower triangular, so it's invertible. Is invertible. And its inverse matrix, well, inverse transition matrix, from the basis V lambda transposed to the basis U mu lies in matrices over integral polynomials of Q. Okay, but the multiplication law in the basis V is independent of O. Right? Last time we argued that in the base V is just, I mean, we argued that V1, V2, and so on, they formed algebraically independent generators. Which we then sent to elementary symmetric functions. Yeah. So it's just a polynomial ring in those, in V1, V2, and so on. And then their products form a basis, and this basis has structure constants independent of anything at all. All right? But then it follows from this that the structure constants in the basis U lie in our ring of polynomials with integral coefficients. And well, this is what we wanted in part 1, right? So theorem 2, part 1 is proved. And it remains to find the degree and the leading coefficient. Okay. So to do this, well, maybe I will erase this theorem, the claim. Anyway, I don't have any more hope that we will prove it today. And I formulate another proposition for that the degree of a lambda mu of t. So this is the, well, this polynomial is at most n of mu minus n of lambda. So once again, n of lambda is the sum I minus 1 lambda I. And the leading coefficient, I mean, of this degree. So it could be 0, but the a priori leading coefficient is equal to the Kostka number mu transposed lambda transposed. So I will later on I will deduce the remainder of theorem 2 from this proposition, just the same way we already argued about the first part of theorem. And now I will prove the proposition, and it will follow from lemma 5. Well, there's some other explicit counting. So let A be an array of a shape mu, weight lambda transposed, strictly row ordered. Then we set d tilde of A is the count of all boxes in mu times mu, such that y is above x in the same column, and A of x is less than A of y, less than A of x right. Then we claim first that d of A plus d tilde of A is equal to n of mu minus n of lambda. And second, d tilde of A is 0 if and only if A is a column So let's prove this. And again, this will be a bijective proof. So as I said last time, it's the combinatorial dream, ideal. When you want to prove an equality, the best way is to construct a bijection. And that's what we do. So brace yourself. Well, we define certain sets that we will count. First of all, ND of A is the number of pairs of boxes again in mu, such that y is lexicographically less than x, and a of x is less than or equal to a of y, strictly less than a of x right. And you see it's something very, very similar, but here it was a strict inequality, and here non-strict inequality. It's this set of pairs of boxes of mu. Now, n of mu is, again, the set of pairs of boxes in mu such that y lies above x in the same column. And it contains d tilde of A, which is the set of pairs of boxes in n of mu, such that A of x is less than A of y, less than A of x right. Now, it is here, but not here, not there. Yeah. Now let's count. Certainly, n of mu is designed so that its count is also n of mu, but small n of mu. Why this is so? This is a question to you. How to count n of mu? So let's count n of mu. Yes. So indeed it will, well, yes, but what will we get? No, 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 no. Right. And so what? Yes, but Yeah. So this is mu transposed 1. Now that is, I don't know how to, well, mu transposed 2. This mu transposed 3, mu transposed 4, transposed 4, and mu transposed 5. Okay, and then each time we just count what? This gives us 3 above it, this gives us 2 above it, this gives us 1 above it.
Давайте посчитаем по строкам просто. То есть в первой строке у нас над всеми клетками 0 клеток. То есть
Okay, yeah, that's a good idea. Yeah, that's a good idea. I agree. Yes.
дальше во второй строке у нас тогда над всеми клетками 1 клетка.
Absolutely, yeah. So Vsevolod is absolutely convincing. So this is the sum of I minus 1 mu I. But on the other hand, if we count by columns, we get the sum of mu transposed I to choose 2. But any of this gives you n of great. What else? The count of d tilde of A gives d tilde of A, just by definition. The count of nd of A gives d of A plus the sum, again, of lambda I transpose choose 2, which is d of A plus n of lambda. This? This? Just
Наберется из меньше либо равно. Вот, но почему оно такое будет? То есть, смотрите, у нас получается, мы можем сказать, что разделим на просто две.
yeah, certainly. One of them gives you d of A, and another gives A of x equals A of y.
Почему там будет именно сумма лямбда и транспонирована?
Because we count all y with the same value as A of x, but the number of x boxes with a given value is just lambda I transposed, right? It's weight lambda transposed. So if we fix the value of A, there are as many lambda I transposed, right? Just we fixed an array of weight lambda transposed. So there are exactly lambda I transposed boxes with the same value of A, right? And then we just count again all the previous, just the same as we argued here. For any box of this filling, we count all the previous boxes of the same filling. It doesn't even matter. We just have some fixed total ordering. Well, it is this total ordering, but it doesn't matter how we defined it. So we ordered. Right, right. And then we just, with each of them, we count all the previous ones. So it exactly gives this count as before. And it didn't really matter how we chose this order. At this stage. Yeah. Okay, this whole argument is due to Andrei Zelevinsky. Okay, so what else? What else do I want to say? Now I want to define a bijection. Phi from ND of A onto N of mu. Namely, let a pair of boxes lie in ND of A, and X has coordinates I1, J1, and Y has coordinates I2, J2. Then, at any rate, I1 is different from I2, and we set I is the maximal value of those two, and I prime is the minimal value of those two, and J is the minimal value of J1, J2. And finally, phi of xy is defined as the pair of boxes I, J, I prime, J. So you see that they do lie in the same column, and this lies above that. So we did land into N of mu. Okay, but sorry, it's not a bijection. It's an injection. Into N of mu, but by construction, phi is a bijection from ND of A onto the complement N of mu to D tilde of A. And hence, A is proved. Pardon me? Just because we know that y is less than x, so what did it mean? Let's recall. In principle, yes. So what does it mean? It's still here, yeah? So they can be, so I1 can be equal to I2 if J, so I1 can be equal to I2 if J2 is less than J1, yeah? Okay. But in this case, we would have so it was J, it was I. Yes, yes. And so this was once again, J2 is less than J1. So this is Y, this is X. Right, but it was strictly row ordered, right? Okay. And we assume that A of Y is at least A of X. Fine. Okay. Now, so maybe we'll have 2 minutes to prove B. So it's A. So I will prove B in 2 minutes, but still I'm afraid I'll have to copy those array notations next time again. So B. This equivalence implication in this direction is evident. And conversely, if A is not column ordered, then there is a box X with coordinates I, J, and a box Y with coordinates I prime J, such that I is bigger than I prime, but A of X is less than A of Y. We choose such a pair with the maximal J, then this pair lies in d tilde of A, and hence d tilde of A is not empty, and its cardinality is not 0, and there we are. Well, so that's it, but unfortunately next time I'll have to recall a lot of notation, and we'll complete the proof of everything. Yeah. Right. No classes on Friday, so you will safely forget everything by next Tuesday. Pardon me? No, we're mostly done. Well, I don't know how to. Yeah. I don't know how to depict a rag. It looks like Coke with a straw instead. I don't know. Okay, thank you. Yes.